So in this lesson, what you've learned so far is that reaction rate can be affected by, there are three different factors that can affect your reaction rate. The first one is temperature. Okay, so the higher your temperature is, the faster the molecules are going to be moving. So you're going to have more collisions, and they're going to be happening with more energy. So they'll have enough energy in order to overcome the activation energy. So you'll have more reactions, the reaction rate will increase. The second thing that affects your reaction rate is the concentration of reactants. So the more reactants you have, the faster your reaction rate, because you're going to have more collisions. Your last thing that affects your reaction rate is your catalyst. So what a catalyst does is it goes in and it lowers the activation energy. The higher your activation energy, the slower your reaction is going to be, the reaction rate is going to be, because you have a bigger hill that you have to get up over in order for the reaction to occur. So what wasn't discussed, though, is the fact that a reaction can actually be reversible. So if you look at this reaction here in front of you, you've got H2 plus I2 producing 2HI. Notice, for the first time ever, you have a double arrow. And what that double arrow tells you is that H2 and I2 can produce HI, but HI can also produce H2 and I2. So if you look at time equals 0, because you only start off with H2 and I2, the reaction rate is going to be pretty fast in the forward direction. But as more and more of the H2 and I2 react with one another, their concentrations are going to be decreased, which means, based on the idea with concentration, as your concentration decreases, your reaction rate decreases. So you see that in red as the arrow gets shorter and shorter. However, as you get more and more product, since that product is acting like a reactant, your reaction rate is going to get faster and faster and faster and faster until you get to the time equals 24 hours, where the rate of the forward reaction equals the rate of the reverse reaction. And at that point, you are at chemical equilibrium. You wouldn't see a change in the concentration of H2 and I2 or HI, because H2 and I2 are going to be used up at the same rate that HI is used up. So there's no change in concentration, because at chemical equilibrium, the rate of your forward reaction and the rate of your reverse reaction are the same. Now, that does not mean that at chemical equilibrium, the concentration of H2 and I2 is the same as the concentration of HI. That's not the case. All chemical equilibrium is telling you is that the rate of the forward reaction, H2 and I2 being used up, equals the rate of HI itself being used up. So the rate of the forward and the rate of the reverse reactions are the same. So we've now taken that concept of your rate of reaction and now said, hey, guess what? A reaction can actually be reversible, and when the rate of the forward and the rate of the reverse reaction are the same, you're at a point which is called chemical equilibrium.
But now we're going to put a number to it. Okay? So the value that we use to describe the state of our equilibrium is called our equilibrium constant. All right? So as always, we can express equilibrium numerically, and we're going to do that with our equilibrium constant. So if I give you a generic reaction like the one you see below, what you will do to find your equilibrium constant, and we represent that with KEQ, okay? Your KEQ, your equilibrium constant, will be equal to the concentration, those brackets mean concentration, so the concentration of C, right, which one of your products, raised to its coefficient, which is the little c, times the concentration of D raised to its coefficient, divided by your reactant, so the concentration of A raised to its coefficient times the concentration of B raised to its coefficient. Okay, so let's look at an example. So it says, determine the value of the equilibrium constant for the reaction below. So it's N2O4 becomes 2NO2. And I give you the concentration of your reactant in your product. So all you need to do to find your KEQ is you're going to take the concentration of NO2, and you're going to square it because the coefficient for NO2 is a 2. And then you're going to divide that by the concentration of N2O4. Okay? So all you need to do now is plug in the values. So it's going to be 0.571 squared divided by the concentration of N2O4, which is 1.5 times 10 to the negative third. And so when you find your answer, it's 220. Okay? I rounded to two significant figures, so it's 220. And that's your answer. Now the question becomes, Why exactly does KEQ matter? Why are we calculating that? Well, that lets us know what we have more of. Do we have more products, meaning our products favored? Or do we have more reactants? Are reactants favored? So before I go to the next slide, which breaks it down for you, if you think about it, you have products over reactants. So if you have more products than reactants, meaning your products are favored, that means your KEQ, your equilibrium constant, is going to be very large. It's going to be larger than 1. Okay? If you have more reactants than products, then that means your KEQ is going to be less than 1. It's going to be a fraction. So let's look at this. Here, if your KEQ, also called your Kc, because we used concentration, if it's around 1, that means you have about equal amounts of reactants and products. Okay? If your Kc is large, right, if it's much larger than 1, what that means is that your products are going to be favored, meaning that your reaction, the forward reaction, is essentially complete because the forward reaction proceeded to produce mostly products, meaning you have very little reactants left over. If your Kc is very small, what that means is that you have more reactants than products, meaning your reactants are favored. So in this case, very little of the reaction actually took place because you have so much reactants when compared to products. So that's what your Kc or your KEQ tells you. If it's really large, that means your reaction proceeded towards the product significantly, right? Your forward reaction did. If you have a very small Kc, what that means is that very little of the reaction actually took place, meaning that your reactants are going to be favored. And if your Kc or your KEQ is about 1, then that means you've got a kind of a typical reaction where your amount of reactants equals the amount of products.